question seems simple enough. We have stars made of matter, so why not stars made of antimatter? It feels like a natural symmetry, a cosmic balance. Our universe is full of particles. Electrons, protons, neutrons. These are the building blocks of everything we know. The chair you're sitting on, the air you're breathing, the stars in the sky. All of it is what we call matter. But for every particle of matter, physics tells us there's a corresponding antiparticle. An anti-electron, also called a positron, an antiproton, an antineutron. These are not imaginary things from science fiction. We've made them in labs. We see them created in high-energy events all across the universe. This stuff, antimatter, is identical to regular matter in almost every way. An antiproton has the same mass as a proton. It just has the opposite charge. A positron is just like an electron, but it's positive instead of negative. So, if you had an atom of antihydrogen, it would have a negative antiproton at its center, and a positive positron orbiting it. It would behave just like a regular hydrogen atom. It would be subject to gravity. It would give off the same light if you heated it up. If you gathered enough antihydrogen gas together, gravity would pull it into a ball. The pressure and temperature at its core would rise. Eventually, nuclear fusion would begin. But instead of fusing hydrogen into helium, it would fuse antihydrogen into antihelium. It would be a star, an anti-star. From a distance, you would never be able to tell the difference. And a telescope looking at an anti-star would see the same light, the same spectrum, as a regular star. The photons of light that a star emits are their own antiparticles, so the light from a matter star and an antimatter star is exactly the same. An anti-star would shine just as brightly. It would live and die just like a regular star. Some would be small and red, others massive and blue. Some would explode in supernovae, creating anti-heavy elements and scattering them into space. The physics is the same, just mirrored. So the original question comes back, are they out there? Are there stars or even entire galaxies made entirely of antimatter? The honest, simple answer is that we don't think so. The overwhelming evidence suggests the universe we live in is made almost entirely of matter. The absence of antimatter on a grand scale is actually one of the biggest mysteries in all of physics. It's a profound problem because, according to our best theory of the beginning of the universe, it shouldn't be this way. Let's go back to the Big Bang. In the first moments of creation, the universe was an incredibly hot, dense soup of pure energy. And from that energy, particles were born. Einstein's famous equation, EMC2, tells us that energy can be converted into mass, and vice versa. When energy turns into mass, it has to follow certain rules. One of them is that it must create matter and antimatter in equal pairs. You can't just create an electron out of nothing. You have to create an electron and a positron at the same time. You can't just create a proton. You have to create a proton and an antiproton. So, in the early universe, for every particle of matter created, an identical particle of antimatter was also created. The universe should have had a perfect balance. Exactly 50% matter, 50% antimatter. For a brief period, this soup of particles and antiparticles seethed. They were constantly being created from energy and then, just as quickly, finding each other. And that's the other crucial thing about antimatter. When a particle of matter meets its corresponding antiparticle, they annihilate. They both disappear in a flash of pure energy, usually high-energy light called gamma rays. It's the ultimate act of destruction and creation. The mass of both particles is converted back into energy, perfectly. So, in that early cosmic soup, electrons were meeting positrons and vanishing, protons were meeting antiprotons and vanishing. As the universe expanded and cooled, there was less free energy to create new pairs. The annihilation continued, and if the universe really was perfectly balanced, every single particle should have found an antiparticle partner. They should have all annihilated each other. The entire universe should have been left with nothing but a sea of photons. No matter. No protons, no electrons, no atoms, no stars, no planets, no people, just light. But that's not what happened. We are here. The galaxies are here. Something is wrong with that picture. The prevailing theory, the one that best fits our observations, is that the balance wasn't perfect. For some reason, still not fully understood, there was a tiny, tiny imbalance. Maybe for every billion pairs of antimatter and matter particles, there was one extra matter particle. Just 1 in a billion. When all the annihilation was over, when all the billion pairs had canceled each other out, that one extra particle of matter was left behind. And that tiny leftover fraction, that cosmic rounding error, is what makes up everything we see today. The entire observable universe, all the hundreds of billions of galaxies, is the remnant of that slight initial victory of matter over antimatter. This idea, known as baryon asymmetry, explains why we live in a universe of matter. It suggests that all the antimatter from the Big Bang is gone. It was destroyed in the first few minutes of the universe's life. In this view, there are no antistars. There are no anti-galaxies. There simply wasn't enough antimatter left over to form them. But what if that assumption is wrong? Science is about questioning assumptions. What if the imbalance wasn't a global thing? What if the universe started out patchy? Maybe some regions of space, by pure chance, ended up with more matter, and other vast regions ended up with more antimatter. In this scenario, the universe could be a cosmic mosaic of matter and antimatter domains. Our observable universe might just happen to be inside a huge matter domain, but far away, beyond our sight, there could be entire superclusters of galaxies made of antimatter. An anti-Virgo cluster, an anti-Laniakea. This is a very appealing idea. It restores a sense of cosmic symmetry. It means the antimatter isn't missing, it's just somewhere else. If this were true, then within those antimatter domains, there would be clouds of anti-gas that collapse to form antistars. Those antistars would group together to form anti-galaxies. It would all look and feel perfectly normal to any anti-beings living on an anti-planet. So we have two competing ideas. One where the universe is all matter, the result of a tiny initial imbalance. And another where the universe is a patchwork of matter and antimatter islands. How can we tell which is right? How do we hunt for an antistar? We already established that looking at its light won't work. An antistar is perfectly disguised, so we have to look for something else. We have to look for the one thing antimatter does that matter doesn't. We have to look for the annihilation. Even if an antistar exists in a separate anti-galaxy far away, that galaxy wouldn't be truly isolated. Our galaxies live in clusters, and those clusters move and sometimes collide. The space between galaxies isn't completely empty either. There's a thin, diffuse gas of regular matter floating around. If a galaxy of matter were to collide with a galaxy of antimatter, the result would be spectacular. The gas clouds from each galaxy would intermingle, protons would meet antiprotons. Electrons would meet positrons. The boundary between the two colliding galaxies would light up with the most intense gamma-ray radiation imaginable. It would be the most energetic event in the universe. We have powerful gamma-ray telescopes in orbit, like the Fermi Gamma Ray Space Telescope. They have been scanning the skies for years. We have seen galaxies collide. It's a common event in the life of the universe. But we have never, not once, seen the telltale gamma-ray signature of a matter-antimatter galaxy collision. The universe is surprisingly quiet on that front. This is a very strong piece of evidence against the separate islands theory. If there were large antimatter domains, we should have seen the fireworks at their borders by now. The smoothness of the cosmic microwave background, the faint afterglow of the Big Bang, also argues against it. This radiation is incredibly uniform in all directions. A patchy universe with matter and antimatter domains would likely have left noticeable hot or cold spots on this map at the boundaries. We don't see them. So the idea of entire anti-galaxies or anti-clusters seems very unlikely. But what about something smaller? What if a few antistars were lurking right here in our own Milky Way galaxy? Maybe some small pocket of antimatter survived and managed to form a star, or maybe a star from a distant anti-galaxy was somehow flung out and traveled across the vast intergalactic void to end up in our neighborhood. This is a much harder scenario to rule out. A single anti-star hiding among the 400 billion regular stars of the Milky Way would be like finding a single needle in a continent-sized haystack. But again, we can look for the annihilation signature. Our galaxy is not empty. It's filled with what's called the interstellar medium. It's a very thin gas of hydrogen and helium, plus a bit of dust. A star, whether it's matter or antimatter, is constantly moving through this medium, and its gravity is constantly pulling this gas and dust towards it. If a regular star pulls in some interstellar gas, not much happens. It just adds a little more fuel to the star. But if an antistar pulls in that same gas, which is made of matter, the result is annihilation. Every single proton and electron from that gas that falls onto the antistar's surface will meet an antiproton and a positron and be destroyed. This would create a constant, faint glow of gamma rays coming from the antistar. It would be like a cosmic bug zapper, so a hypothetical antistar in our galaxy should be a point source of gamma rays. Our telescopes have scanned the galaxy in detail. We have found many sources of gamma rays. They come from pulsars, black holes, and other violent cosmic objects, but their energy signatures don't match what we'd expect from matter-antimatter annihilation. Annihilation produces gamma rays with a very specific characteristic energy. We haven't found any point sources that fit this profile perfectly. Based on the lack of these signals, astronomers have been able to set limits. They can say with some confidence that, for example, there is less than one anti-star for every million normal stars in our galactic neighborhood. The more we look and find nothing, the more we can shrink that possibility. It seems our own galaxy is also made purely of matter. But the hunt isn't completely over. There is another way to look for evidence of antimatter, and this is where things have gotten very interesting recently. Instead of looking for the light from annihilation, we can try to catch actual particles of antimatter flying through space. These particles are known as cosmic rays. Space is filled with high-energy particles zipping around, left over from supernovae and other events. Most of them are protons and atomic nuclei, but a few are antiparticles. We expect to see some antiparticles. For instance, when high-energy cosmic rays, which are matter smashed into interstellar gas, also matter, the sheer energy of the collision can create new matter-antimatter pairs. So we expect a certain background drizzle of positrons and antiprotons created through these secondary processes. This is normal. It doesn't mean there are antistars, but it would be extremely difficult for these collisions to create anything more complex than a single antiproton. For example, creating an antihelium nucleus, which has two antiprotons and two antineutrons, is incredibly unlikely. The odds of four antiparticles being created in the same place at the same time and sticking together are astronomically low. So, if we were to find just one anti-helium nucleus flying through space, it would be a bombshell. It would be very hard to explain its existence from normal cosmic ray collisions. The most straightforward explanation would be that it was forged in the core of an antistar and blasted out into space. This is where the Alpha Magnetic Spectrometer, or AMS, comes in. It's a particle detector that sits on the International Space Station. Its job is to catch cosmic rays and identify them. It's a fantastically sensitive instrument. Over the last decade, it has analyzed billions of cosmic ray events. It has measured the background of positrons and antiprotons with incredible precision, helping us understand those secondary production processes better. And it has also been looking for heavier antinuclei. In recent years, the AMS collaboration has announced that they have detected a handful of events that look like they could be antihelium nuclei. This is a stunning claim. If it's true, it could change everything. It would be the first real evidence of macroscopic objects made of antimatter existing in our universe today. However, and this is a very big however, the scientific community is still extremely cautious. Identifying these particles is incredibly difficult. There are many ways the detector could be fooled. A regular helium nucleus might interact with the detector in a weird way that makes it look like an antihelium nucleus. The number of candidate events is tiny, less than 10 out of tens of billions of particles. The team is still working to rule out all possible sources of error. No one is claiming victory yet. Even if these anti-helium candidates are confirmed, it still doesn't automatically mean there are antistars nearby. There could be other, more exotic explanations. One idea involves dark matter. Some theories suggest that when dark matter particles collide and annihilate, they could, under very specific circumstances, produce matter and antimatter pairs, including the occasional anti-helium nucleus. So even this potential smoking gun might be pointing to a different mystery altogether. So where does that leave us? The big picture is that the universe appears to be overwhelmingly dominated by matter. The lack of annihilation signals from the edges of galaxies and galaxy clusters is a powerful argument against large antimatter regions. The lack of gamma-ray point sources in our own galaxy makes it highly improbable that antistars are common or even present at all in the Milky Way. Our standard model of cosmology, with its tiny primordial imbalance, does a good job of explaining this observation. It's the simplest and most elegant solution, and yet the question won't go away entirely. The possibility, however small, remains. The AMS experiment has opened a tiny crack in the door of our certainty. Those few potential antihelium events are tantalizing. They force us to keep looking and to keep an open mind. They remind us that the universe is under no obligation to be simple. The search for antistars is more than just an astronomical curiosity. It's a search for the answer to one of the most fundamental questions about our existence. Why are we here? Why did matter win? Why is there something rather than nothing? If we found an antistar, it would mean our understanding of the Big Bang is incomplete. It would suggest that the universe is far stranger and more complex than we imagined. It would mean that somewhere out there is a looking-glass version of our own cosmos, a place where positive charges orbit negative nuclei and anti-galaxies spin in the dark. But if, after decades more of searching, we find nothing, that absence is also a profound discovery. It tells us that the universe really did make a choice in its first moments, that the tiny asymmetry that allowed matter to survive is a fundamental feature of our reality. It would mean that the stuff we are made of is truly special, that we are the lucky leftovers of a cosmic war where almost everything was annihilated. The fact that we could even build the tools to ask the question, to scan the skies for the faint gamma ray whisper of a mirrored star, is a testament to that primordial victory of matter over its opposite. For now, the stars we see are the only stars we know, and they appear to be made of the same stuff as us.